Welcome to Cloud on Air, live webinars by Google Cloud. We host webinars every Tuesday. I'm Manjot. I'm a product manager on Google Cloud, and today I will be talking about enterprise networking for containerized applications. Feel free to ask questions anytime on the platform, and there will be Googlers to answer them. Let's jump right in. So what's on the agenda today? So the first thing we will be talking about is what is the difference? What are containers, and what is the difference between containers and the older deployment models like virtual machines? And how that difference affects your networking. The second thing we will be talking about is introducing you to basic concepts about Kubernetes networking. And the third thing that we will be talking about, which will form the majority of this presentation, is what are some of the best practices? What are some of the controls you have such that you should not only actively deploy them, but you should also maybe even make them the default deployment pattern in your containerized applications. So in front of you, you see three models. The first one being bare metal, which is probably the oldest, way to deploy a web application. So bare metal obviously consists of a physical server, a host OS, and then you deploy your applications on top of it. Clearly, this has a lot of disadvantages, such as there's no isolation between your apps. They share libraries. They're highly coupled to the OS. So this definitely leads to a lot of problems. Then came VMs. So VMs are based on the physical server. There's the host OS, and then there's the hypervisor layer. This hypervisor layer then enables you to have VMs on top of it, and then you deploy your applications inside those VMs. And every single application consists of a guest OS. This way you achieve much better isolation. There are no common libraries shared across the different applications. However, you can still see that managing a VM is still inefficient. It's still very expensive. Simple operations like auto-scaling, etc., definitely take way longer. So you definitely see you still see a lot of disadvantages with the deployment model of a virtual machine. Next step in this evolution was containers. So the way you go about for containers is you have a physical server, then you have a host OS, and then you just deploy your apps. You deploy your apps on top of it without having this need for a guest OS within every single application. The way you do this is via the fact that containers use kernel level features, and so you achieve much better isolation in your applications. There are no common libraries that are shared. There's way less overhead. There's definitely less dependency on the host OS, and they're not as tightly coupled to the host OS as they are in the previous cases. And the fact that you don't need a guest OS within your containers is what makes them so reliable, so efficient, so lightweight, such that you can easily deploy them in multiple models. And hence, this is why we see modern web applications migrating towards containers. By a popular report by Diamanti in July 2018, it was found out that around 12% of applications, 12% of applications by enterprises already are containerized, and another 47% want to containerize. So there's definitely a lot of interest in containers. So Kubernetes was launched, clearly. So in 2014, Kubernetes, which is a portable, open source, container-centric management platform, was launched. So when you have containerized applications, you definitely need some sort of an orchestrator on top of it to actually manage those containers and make some of the and relieve you of some of the infrastructure level operations that are needed. So Kubernetes started off as a simple container orchestrator, but eventually became a container-centric management platform with built-in primitives for things like deployments, rolling upgrades, scaling, monitoring, and much more. So Kubernetes was inspired by Google's internal systems, very popularly known as Borg. So we've been running containers for over 15 years. So one of the philosophies guiding Kubernetes was workload portability. and increase infrastructure efficiency such that we relieve you from a lot of these common infrastructure operations. One of the biggest advantages that Kubernetes has is the fact that there is a really well-organized community around it. This is the reason why we see a huge adoption of Kubernetes, not only in cloud-native companies, but also in the enterprises. So why are we here? So one of the biggest things we saw was container adoption itself is recent enough, and also Kubernetes is pretty new. So a lot of practitioners were not aware of some of the networking controls we have, some of the networking defaults they should be setting in their applications. And by practitioners, I mean network admins, network engineers, developers, security admins. So the purpose of this whole presentation is to make you aware of some of those best practice, some of the controls that you have in your hand, which you should be making the default in your deployments. So before we jump right in, a little overview of some of the basic concepts of Kubernetes and Kubernetes networking. So Kubernetes cluster, which is a single deployment that you can have, consists of pods, nodes, and services. A pod is the single unit of deployment within Kubernetes. A node roughly translates to a VM. And within a single node, you have several pods, a maximum of about 110 that you can have. And services is another Kubernetes native concept, which is basically an abstraction over a set of pods. So this way, you can create multiple services within your Kubernetes cluster and assign labels to your pods, indicating that they belong to a specific service. Since the pod is a single, is the atom of deployment for Kubernetes, a pod has a single IP address. And Kubernetes follows a flat networking model, which basically means every pod can talk to every other pod on that single cluster. As we move along, and I tell you more about some of the controls you have, things will start to make a lot more sense, and you'll actually understand why it has been architected the way it has. So jumping right into some of the best practices that you should be deploying in your Kubernetes clusters, the first thing we will talk about is container native load balancing. So in front of you, you see VM-based or a traditional load balancer-based load balancing. And what we see here is basically your load balancer sends a request to one of the nodes in the cluster. When the request reaches a single node through IP tables rules, it goes to the actual pod, which is a part of the service where you wanted to navigate your request to. So this way, if a pod is in a different node, what happens is your request has to jump through two hops, where it comes to a single VM, and then it might go to another VM if the pod where the request goes eventually is not on the same VM. This obviously leads to suboptimal load balancing, considering there are two levels of it: one at the node layer, and one at the one when it reaches the first node, and one it actually reaches the pod which serves your request. You also get suboptimal health checks which work at the VM layer, and you can clearly see that there are multiple network hops. This might even affect your end user serving latency and several other problems that you can imagine. Moreover, another thing to note here is that since requests might move from one node to another because of complex natting, denatting rules, you might also lose some of the visibility into your containerized application. So clearly, we see that the unit of compute or the unit of deployment for web applications move from virtual machines to containers. But we see, at least till now, we saw load balancers lagging in being able to understand that container as a first-class endpoint. So now today we introduce container native load balancing. What is container native load balancing? Container native load balancing basically has the aim that we establish containers as first-class endpoints, such that there should be no difference between a virtual machine and a container endpoint. So we introduce this concept called network endpoint groups. What does network endpoint groups do? So you basically, if you follow the request path in front of you, you see that the request now comes in from the load balancer and goes directly to the pod. There is no proxy in the middle. There is no IP tables routing. Kubeproxy is not involved in this process. It's a clean data path where a request comes in from the load balancer and just goes to the pod, which is actually supposed to serve your request. The way we achieve this is via network endpoint groups, which consists of a list of endpoints where a single endpoint is an IP port pair representing your pod. This way, containers become just another endpoint. You get accurate health checks and you get accurate health checks which work at the pod level, and your load is much more evenly balanced over your pods. There are no extra network hops, which obviously gives you much better network performance. And also there's a direct connection from the load balancer to your pod, which gives you better visibility and better troubleshooting for your services. So looking at the two models of deployment side by side, now we see the difference between how much more simplified the data path is with container native load balancing versus how it works in a traditional load balancer. Another thing I would like to definitely point out here is there are definitely some solutions which have tried to resolve the same problem, where you install an agent on every single node, and then that agent is responsible for load balancing over those pods. But the underlying problem was the fact that containers were not first-class citizens for the longest time when it comes to load balancing or many other applications. So what we did was, within our networking fabric itself, establishing containers as first-class citizens. And this is available on both Kubernetes on Compute Engine and Kubernetes Engine. So summarizing some of the benefits you have with container native load balancing, the biggest aim with container native load balancing was establishing containers as first-class citizens when it comes to load balancing. This leads to much more evenly balanced load. It unlocks a host of advanced load balancing algorithms that you can use and enables you to do things like traffic shaping. When you compared the two images of traditional load balancer and a container native load balancer side by side, you could see the difference in the data path, where initially the data path was so complex, where it went to one VM, then it went to IP tables, and then it went to another VM potentially. And now if you see the data path, it's clean, where it goes directly from the load balancer to the pod. So this eliminates a lot of overhead in terms of IP table routing. It leads to more predictable network performance, might even give you reduction in latency. And the last biggest advantage of network endpoint groups and container native load balancing is much better visibility into your deployments. Just because your request is not going from one VM to another, you don't have those complex natting, denatting rules, and you get accurate health checks. So this is one of the settings that we definitely recommend for you to have by default. Moving on to the second biggest setting that you have, the second, not biggest, but like one of the biggest settings you have in your hands is container native visibility. So one of the things that we launched some time back was VPC flow logs. What are VPC flow logs? So VPC flow logs are basically flow log records for your cluster, where we try to ensure that every single request path is covered. What do I mean by covered? That every single request that flows within your VPC produces sampled flow log records. So if you look at the diagram, you can see all the green arrows basically represent all the request paths that are covered, whether it's traffic coming to your cluster from the internet, whether it's traffic going from your load balancer to your services, whether it's traffic flowing between your services, or the traffic between your pods. There is also the traffic that flows from your on-prem deployments or on-prem clusters to your Kubernetes Engine clusters. And also, if you're using any GCP managed services like BigQuery, Dataproc, Cloud Pub Sub, or any other, you again have VPC flow logs for those requests. One of the biggest differentiators for container native VPC flow logs is the fact that our flow logs are aggregated in nearly real time every 5 seconds versus minutes. That is the usual case. And again, you notice here that our flow logs are basically not agent-based. Usually, you have agent-based solutions where an agent sits within a single node and is responsible for generating those logs. So you see the fact that we are trying to ensure that all of these things work natively within our networking fabric. Some of the other properties of container native VPC flow logs that I should definitely call out are the fact that it includes ingress and egress and is enabled for the whole subnet. So it covers all the VMs within a single subnet. Also, it covers both TCP and UDP flows and works across some of the first-class features that you have on hand, such as shared VPC, VPC pairing, and also works with things like ILB. What exactly are VPC flow log records? They're a standard 5-tuple source IP, destination IP protocol. It includes metrics like bytes and inferred RTTs for all the TCP flows. And it includes a host of VPC annotations that might be useful for you, such as the region or zone, and so you can aggregate on top of that. So VPC flow logs, what are some of the applications? Like, why would you even need VPC flow logs? VPC flow logs obviously give you a lot of visibility into your deployments, and you can actually use that raw VPC flow log data to build a host of applications or a host of functions on top of it to figure out analytics and things within your clusters. So some of the typical applications we see are around optimizing network usage and egress. We also integrate with a host of partners such that you can use a monitoring tool of your choice and just export that raw data from VPC flow logs to that engine. Some of the other applications are around network forensics, so you can do traffic pattern analysis to catch bad actors. Also, since I already mentioned that VPC flow logs are aggregated in near real time, you can actually do real-time security analysis. Some of the other things that you have in your control are you can actually export that raw data using Cloud Pub Sub to things like Stackdriver logging or BigQuery or any other monitoring tool of your choosing. Moving on to the third setting, which is container native network policy. So let's start with a brief history of what firewalls actually look like with a traditional VM. So if you look in front of you, basically you had users coming in and talking to your load balancer, and there was a firewall on that load balancer. Applications typically ran on dedicated machines. There were these monolithic applications. Firewalls were usually applied on IP ranges. And typically the firewall itself was applied directly at the network layer, sometimes even a physical device. So you can obviously imagine how static that environment could be. Changes would take a long time. It wasn't as dynamic as you would like it to be. Also, you can clearly now imagine how this model cannot be applied for containerized applications, because now your unit of deployment is a pod, and that pod might be spread out across several VMs. And this can lead to, this basically tells us that we need a separate model of deployment for network policy for containerized applications. Enter network policy. So now, instead of applying network policy at the network layer, we have a microservices-based network policy application. So this actually enables you to have microsegmentation for your services, where you tell exactly which services can talk to which other services. The enforcement is done when different pods talk to each other belonging to different services. So you can actually break down your monoliths into smaller pieces. You have durable APIs between your services, and the network policy agent can actually handle a large amount of churn for pod IPs that is typical of Kubernetes. Some of the things to be aware of is, so network policy, as I mentioned, is a first-class Kubernetes native concept, which enables you to have a user-defined policy where you specify which services can talk to which other services, or which services have access to which other services. It is enforced in real time via a policy agent that sits within every single node, and ensures that you have the micro-segmentation that you expect. Why would you even need network policy? So let's say you have an application where you have front-end pods, you have back-end pods, and then you have another services which is processing payments. So ideally what you would want is, if you have compromised front-end pods, you wouldn't want to have compromised payment services. So this basically, network policy actually enables you to have that behavior. Moving on to the fourth set of common practices that we recommend are around some of the network services that we have in GCP. So container native network services, we all know that ingress is how we typically configure our load balancing, our host path routing rules at L7. The changes that we have brought about recently within Kubernetes Engine and GCP are around configuring some of the other network services that we have and bringing them to your containerized deployments. So some of the use cases that enterprises typically have are having protection against denial of service attacks or other application attacks at L7. You obviously want identity-based access control for your internal applications, and some of the other features that you might want is a global caching infrastructure, so that no matter where your users are, we ensure that we serve as less latency as possible for your containerized applications. Some of the other things that you definitely want in your modern web applications, which is microservices based, is support for newer protocols such as gRPC. So keeping all these use cases in mind, we basically came up with a host of services that would help you achieve all these goals. We introduced the concept of a backend config. What backend config enables you to do is, on a per service basis, it lets you specify which network services within Google Cloud Platform you would like to use via ingress. So this ensures you satisfy your use cases around application layer security. You also can use identity-based authentication at application granularity for your internal apps. You can use backend. So backend config is basically a Kubernetes native resource which ensures that services are a first-class concept when it comes to these settings. And all of these are integrated natively with our GCP network services. Moreover, you can use modern protocols like HTTP2 and gRPC. So summarizing some of the benefits around container native network services. So you have flexibility to configure all these services on a per service basis, which enable you to do things like traffic shaping and being able to block DDoS attacks, identity-based control for your applications. Moreover, you can use some of the newer protocols such as HTTP2 and gRPC for your modern web applications. So moving on to the fifth set of settings that you definitely want within your deployments or container native around our VPC or our virtual private cloud. So shared VPC is basically a model of deployment which enables you to get have developer velocity while not compromising on your enterprise administrative control model. What does that mean? So basically, in a typical enterprise, what happens is there's a platforms team which wants to control things like firewalls, peerings, and other very, very critical network resources. And then you have some application teams as well, some application teams that want to still create and manage their Kubernetes clusters. So how do you achieve this enterprise organizational model within your network? The answer for that is shared VPC. Shared VPC works on this model of that there's a host project which actually consists of your shared VPC network, And then there are service projects within that host project. The service projects, which exist within the shared VPC subnets, have only use permissions over the shared VPC. And that enables them to create, manage, deploy their Kubernetes Engine clusters. Whereas your network admin, your security admin, still has control over admin controls over the shared VPC itself. So they are the ones that actually manage those critical network resources. So clearly you see a host of improvements with this particular model of deployment. You see that despite there is still separation of roles that typically exists within an organization. This is how you can basically achieve isolation between who has admin permissions and who has only use permissions. It also enables you to still share common resources across all those different subnets, and across all those different clusters, while not compromising on the fact that security and separation of those roles is a critical feature as well. The other thing that shared VPC gives you is isolation of data and support for all your multi-tenant workloads. You can basically compartmentalize your applications into different projects that exist within different service projects in the host project shared VPC network. It also gives you much more granular billing, such that you can actually view billing on a per project basis in the service projects. So moving on to the next default setting for your Kubernetes Engine deployments is private clusters. So one of the things that, so security is definitely one of the things that is very critical for all your web applications, all your Kubernetes and Kubernetes Engine deployments, and front and foremost for us as well. So one of the things that we worked on is private clusters, which enables you that your Kubernetes Engine cluster is within the trusted boundary of your VPC. What does that mean? So in the past, all your Kubernetes nodes used to have public IPs. This was done so that end-to-end management of your Kubernetes Engine managed cluster becomes easier for us. But since we have some of our, because of our advanced peering capabilities now, that is no longer a requirement. So private clusters takes your Kubernetes Engine cluster off the public internet by removing all the public IPs on your nodes. The communication between your nodes and the Kubernetes master becomes completely private, and you can cordon off your master using a whitelist with a set of IPs that you control using master authorized networks. This way, only a trusted set of IPs from your on-prem or a trusted set of IPs within your VPC have access to your nodes and your master, blocking away unauthorized, untrusted accesses. So this is again one of the things that we definitely recommend customers have in their deployments. Quickly summarizing all the things that we discussed here today. Kubernetes Engine basically wants to establishes containers as first-class endpoints, and some of the settings that we definitely recommend for you to have in your Kubernetes Engine and Kubernetes cluster include things like container native load balancing, which gives you much more evenly spread out load for your load balance applications. Enabling container native pod-to-pod flow logs, which gives you much better visibility of your network traffic. Container native network policies, which are enforced at the scale that we promise, which is 5,000 nodes, which ensures which services can only certain services can talk to certain other services that you control. And seamless integration with some of the container native network services, which definitely enhance some of the applications that you want in your containerized web apps. And some of the other settings that we recommend would include private clusters or container native VPC, such that your deployment is within the trusted boundary of your VPC. So stay tuned for the live Q&A. We will be back in less than a minute. Welcome back. Some of the questions from our audience. How do I enable negs in an existing containerized application? So it's basically through upgrading your ingress controller and also setting an annotation within your service that lets you enable negs. After that, it just works automatically. Can I get VPC flow logs into my custom monitoring tool? Yes. Definitely yes. We definitely integrate with a host of third-party monitoring tools as well. And you can export VPC flow logs through Cloud PubSub to a monitoring tool that you choose. Are there any differences in networking between hosted Kubernetes in GCP and GKE? Yes, there are a host of features that work only with Kubernetes Engine versus Kubernetes that you manage on Compute Engine. So we would definitely recommend using Kubernetes Engine managed clusters for several of the applications, for several reasons that we have. And it's not just networking related features that we would say are relevant here, but also several other features that are available on Kubernetes Engine versus only Kubernetes on GCE. Can you elaborate on the usage of shared VPC for a multi-tenant application? So basically, shared VPC works on the concept of there's a host project which actually consists of your shared VPC resources. Within those shared VPC resources are subnets. Within those subnets is when you create service projects. So a service project is basically one which is controlled by a cluster admin, and a cluster admin has permissions on that service project and on that subnet. Moreover, another thing to note here is that that service project admin does not have modify or editor permissions on that shared VPC or the subnet. They only have use permissions, and if you want, you can give more permissions, obviously. But usually you want to give only use permissions over that subnet, so that you have this separation model of the network admin controlling critical network resources and the cluster admin being able to create, manage, and deploy clusters. This way you can separate out your tenants into the host project and the service project model to get that kind of an isolation. That's it. Well, stay tuned for the next session on shielded VMs.